For our first example of centers of mass, or centroids of a lamina, let's take a look at this particular region. So if we had y equals 1 over x, y equals 0, so the x-axis, and we're looking at it between the two vertical lines, x equals 1 and x equals 2. So I jumped over to Desmos and I graphed this y equals 1 over x, and I shaded the region that our lamina is being defined by. So just a quick reminder, lamina means that we have a plate essentially of it's infinitely thin and it has uniform density. So those two pieces are important for our case here in Calc 2, and then we can vary the density when we get into multivariable calculus, into Calc 3. So this particular case, so if we wanted to find the centroid, which is the center of mass of this particular type of plate, then we can utilize the formulas that we derived in the video on centroids and center of mass. So I captured that image of those formulas that were derived, and we can go ahead and start working this out. So the first thing that I would suggest that we do is that we actually find A. So if we go ahead and find A is going to represent the actual area, integral from 1 to 2 of 1 over x dx. So let's find that, and then we can carry that constant throughout and put that into our integrals for x bar and y bar. So integral of 1 over x dx, of course, is just the natural log of the absolute value of x evaluated from 1 to 2. So it turns out that A is actually just equal to the natural log, the constant, the natural log of 2. All right, so we'll utilize that because our x bar formula and our y bar formula use that constant 1 over a, and y bar, it's 1 over a times integral from a to b of 1/2 f of x squared dx. Both of those use that. So calculate that first, and then we can jump into the calculations for x bar and y bar. So x bar is going to be 1 over a, and I'll plug that in after I calculate it. 1 over a times the integral from 1 to 2 of x times f of x, but we're looking at the function 1 over x dx. And so that's going to end up just being 1 over a times the integral from 1 to 2 of 1 dx, which is just 1 over a times x evaluated from 1 to 2. So x bar ends up being 1 over a times 2 minus 1, or 1 over a, which we calculated a up here. A was just the natural log of 2, and this is going to be 1 over the natural log of 2. Okay, so 1 over the natural log of 2, if we actually were to get that, and I want to go back to the graph here in a second. So x bar is approximately at 1.44. So the center of mass, the x coordinate, is approximately at 1.44. And then we would want to find the y coordinate. So to find the y coordinate, y bar is going to be 1 over, over here, if you take a look back at our formula, it's 1 over a times the integral from a to b of 1/2 f of x squared. So I'm going to put the 1/2 and the 1 over a together and write this as 1 over 2a. That's another way to express the formula. Integral from 1 to 2 of the function, which was 1 over x squared dx. And then we'll find that that's going to be 1 over 2a times the integral from 1 to 2 of x to the negative 2 dx, and then that integral is 1 over 2a times negative x to the negative first, evaluated from 1 to 2, and y bar is going to be equal to 1 over 2a times negative 1 over x, evaluated from 1 to 2, 1 over 2a, we've got minus 1/2 plus 1. And so this ends up being 1 over 4a. Okay? So we end up with 1 over 4a. Again, we calculated a at the beginning. A was our just the area of the region. So a is the natural log of 2. And we end up finding that y bar equals 1 over 4 times the natural log of 2, which is approximately, I did that on my calculator, approximately 0.36. So doing those on the calculator, that was my y bar, and 1.44 was my x bar. So my actual center of mass, and I just wanted to come back to the picture here, my actual center of mass, or my centroid of this lamina, this infinitely thin plate of uniform density, is actually approximately equal to, rounded to 2 decimal places, 1.44 and 0.36. So just as a note, what does that mean? That means that's the place where if we were to place a balancing, if this lamina needed to be balanced, if we could place like a toothpick right underneath this this screen of this plate, we would place it at 1, so 1.44, so a little less than 1.5. So that would be somewhere in here, and 0.36. So let's see, 1, 2, 3, 4, 5. So each of these, so somewhere like right about here would be my x bar and my y bar. That's right where this mass, this center of mass, where this object, this flat plate would be balanced, exactly, perfectly balanced at that center. So that is our first example of centers of mass. And I think I'm going to hold off and we'll do more examples in either another video or possibly in our class session.